Okay, so in the previous videos, we saw how to find the cascading capacity of the network based on the cascading capacities of the clusters of the network. Now, this is possible if we can clearly identify the clusters within a network. Now, what if we cannot identify the clusters within a network? Again, when you say a cluster, again, it should satisfy the modularity definitions and so on. That should be more edges within the cluster than edges to nodes outside the cluster and so on. So what if we cannot really have such a thing in a network? So one strategy is to find what is called the minimum character dominating set of the network. It's a set of nodes such that for any node in the network, a node is either in the MCDS or is connected to a node in the MCDS. Okay. So for example, for this network, we can say 134 will form an MCDS because um, for every other node, at least one of the nodes is in the MCDS. At least one of the neighbor nodes is in the MCDS. Now, whatever you try on this graph, you cannot find MCDS or of size less than 3, say for example 2. You cannot pick two nodes and say for every node either the node is in the MCDS or is connected to a node in the MCDS. Okay. So how to find the MCDS of a network, right? We'll see that little later. Now, how to use the MCDS to compute the cascading capacity of the network. So that's what we'll see first. So the solution is quite simple. We'll first find the MCDS of the network and we'll assume that all the MCDS nodes, again MCDS is kind of going to be a very small set of nodes compared to all the number of nodes in the network. So it is okay to assume all the nodes that are part of the MCDS to be initial adopters. And since by definition for an MCDS the neighbor nodes for nodes that are not in the MCDS, at least one of its neighbor nodes will be in the MCDS. So for nodes that are not in the MCDS, we are going to find what fraction of its neighbor nodes are in the MCDS. Okay, so that is the cascading capacity of a node. So the cascading capacity of a node that is not in the MCDS is the fraction of its neighbor nodes that are in the MCDS. And the cascading capacity of the network is the minimum of the cascading capacity of any node in the network. So for example, given this network, we see that 134 will be the MCDS. So for the other nodes, what fraction of the neighbor nodes are in the MCDS? For node 2, all its 3 neighbors are in the MCDS. So the cascading capacity of node 2 is 1. For node 5, one of its 2 neighbors is MCDS, so the cascading capacity of node 5 is 1 half, 0.5. Similarly, for node 6, one of its 2 neighbors is an MCDS, so its cascading capacity is 0.5. So now the minimum of 0.5, 0.5 and 1 is the cascading capacity of the network. Similarly, say in this example here, W, X, U and V are the MCDS. Okay, so given that W, X, U, V are MCDS, go ahead and find for the other nodes what fraction of their neighbors are the MCDS. So for this node here, 2 of its 4 neighbors are in the MCDS, so its cascading capacity is 2/4. For this node here, 1 of its 4 neighbors are in the MCDS, so its cascading capacity is 1/4. And the minimum of all the cascading capacities of the non-MCDS nodes is 1/4. That is the cascading capacity of this network. Now you may be wondering, is that revealing the maximum cascading capacity possible for a network? The answer is no, because MCDS based approach gives you a kind of a lower bound for the cascading capacity of a network. But it's a guaranteed value in the sense that if you choose these MCDS nodes as initial adopter within one iteration, every other node can adopt that decision. Okay, so you don't have to go through more than one iteration with an MCDS based approach. But the cascading capacity is kind of like a lower bound in the sense that we could choose fewer nodes as the initial adopters and come up with or go through iterations and using a cascading capacity or using the Q value that is kind of larger than what we find from the MCDS based approach. So that's what I list as the pros and cons of using the MCDS approach. So the MCDS approach gives you a lower bound for the cascading capacity of the network, as it enables a node to adopt a decision just if even one of its neighbors have adopted the decision. So that's what you see in this example here. This node will adopt the decision, or its cascading capacity becomes 1/4 because at least one of its neighbors have adopted the decision. So that is the kind of advantage for the information to just penetrate to the entire network. So there's no need for more than one iteration. Once you determine the MCDS, you determine the cascading capacities of the non-MCDS nodes, and then based on that you can determine the cascading capacity of the network. On the other hand, the weakness is if you reduce the number of initial adopters compared to the number of nodes that are part of the MCDS, you will be able to find a relatively larger cascading capacity of the network by going through some iterations. Again, I said we will be, but I have to take it back. We could find a relatively larger cascading capacity for a network by going through one or more iterations. Again, it's not guaranteed though that we'll complete the cascade, but with the MCDS approach, yes, we can complete the cascade. Okay. Now, again, as we go through more than one iteration, by choosing fewer initial adopters and a larger cascading capacity, you have to consider all the cluster densities and all those stuff, as well as the adoption will slowly spread. It cannot just penetrate like this example here. It will just spread like this, and then this. Okay. So that's the negative or weakness of MCDS approach, that it gives only a lower bound for the cascading capacity. But the advantage is in one iteration you can have complete information cascade. Now, how to find the MCDS of a network? So we'll go to this example. So again, by definition, MCDS means the minimum set of nodes that are connected to each other, in the sense that every node in the network is either in the MCDS or is a neighbor of a node in the MCDS. So that means you want to cover as many nodes as possible by including a node in MCDS. So given a graph like this, we'll find the number of neighbors for each node, which are listed out here, and you'll prefer to include a node that has a larger number of neighbors. So in this case, we could include either G or J, and we break the tie in favor of the lower alphabet, so I pick G. So when I pick G, G covers 6 of its neighbors. Okay. So we say now the covered nodes, which are the 6 nodes, are the candidates for inclusion to MCDS in the next iteration, because you want a connected set of nodes that are part of this MCDS, so that the nodes are reachable to each other. So this is what we do. G has no, so you see now G we say 0 because that's the number of uncovered neighbors. So to begin with, every node is not covered. So the degree of a node is same as the number of uncovered neighbors. Now with these 6 nodes being covered, look at node D, both its neighbors are covered, whereas initially both its neighbors were not covered. So now for node D, the number of uncovered neighbors is 0. Now for node P, only one of its neighbors is covered and one neighbor is not covered. So the number of uncovered neighbors for node P is 1. Now for node N, the number of uncovered neighbors is M and 0, so it's 2. So you redo the calculations for the number of uncovered neighbors. And now among the covered nodes, which are colored in yellow, pick the node that has the largest number of uncovered neighbors, which is in this case going to be node J, and because of this, J will now cover F, I, M, N, and O. So those nodes are also considered as covered nodes. So redo the numbers for the number of uncovered neighbors, and among these covered nodes, pick the node that has the largest number of uncovered neighbors, which is B. It is the only node that has 2. Everything else has 1 or 0. So B is now getting picked up, and as you can see, you are maintaining the connectivity among the nodes within the MCDS. So B can now connect to G as well as to J through G. So that's the connectivity I'm talking about among the MCDS nodes. So now redo the numbers. You see now it could be C that has one uncovered neighbor, which is D. So 1 and 0 are the values, so you pick 1, and we have a tie, we pick C instead of H because of the alphabetical order. So now everything else is covered other than P. So in order to cover P, you have to either pick L or O. So we'll pick L, alphabetically lower, so that will cover P. So these are the 5 nodes that are part of the MCDS. We can see they are reachable to each other, they are connected to each other. Now, using these 5 nodes as the MCDS nodes, we'll go ahead and find the cascading capacity of the other nodes in the network. So for a non-MCDS node, its cascading capacity is the fraction of its neighbor nodes that are in the MCDS. So for example, for node A, it has 2 neighbors, and one of its 2 neighbors is in MCDS, so its cascading capacity is 1/2. Similarly, for node D, it is 1/2. Now for node H, it has 4 neighbors, and 3 of its 4 neighbors are in MCDS. So cascading capacity of node H is 3/4. So like that, you find the cascading capacities for every node in the network and take the minimum of these values, which is 1/4. So that is the cascading capacity of this network based on MCDS approach. So stop the video with this.